The purpose of this video is to provide a step-by-step description on how you can implement a groundwater model using INOWAS platform. So as a case study, we choose the case study of Ezousa catchment. So basically, we start by introducing Cyprus, the location of Cyprus. For the ones who don't know where Cyprus is located, it's an island located at the east part of the Mediterranean Sea. And the Ezousa catchment is located at the southwest part of Cyprus, next to the coast. So it's a coastal aquifer, as we can see. And the purple lines that you see here define the computational domain of our case study. As a starting point for our model, we are using this aerial view of the region. As you can see here with the dashed red lines, this is going to be considered as the computational domain. So the starting point of our model is based on the visualization of this aerial view, which is georeferenced based on the WGS84. Some few details that will be used during the modeling of the catchment. So as you can see, there is a distribution of the hydraulic conductivity, which has the lower values close to the coast, and it's monotonically increasing as we move further away from the coast. And you see that the specific yield is around 11%, the porosity is around 20%. So these values here will be considered during the calibration of the model. And what we show here are the system boundaries based on field measurements. We have decided to impose no-flow boundary conditions at the north and south parts of the domain. And regarding the coastal boundary, we are using the CHD boundary conditions, which means we specify hydraulic heads. And due to the fact that this boundary is very close to the sea, as a boundary condition, we are choosing a constant hydraulic head equal to 0. Now, regarding the uppermost boundary condition, we are again using the CHD boundary condition, the time-specific hydraulic head condition, and the values for this boundary condition are determined based on the observations of a nearby well. Now, in the current video, we are going to focus on the steady simulation. Other boundary conditions such as infiltration through infiltration bones or extraction through wells will not be considered to the computations. We expect to develop a model that will take into account these dependencies in the next few months. And just another information is that in order to digitalize the computational domain and all the components of the model, we are using the QGIS. As you can see here, we have already developed the ponds, the wells, the different regions based on the conductivity zones, based on previous works related with Ezousa catchment. So now we start talking about the implementation of the model in the platform. So here I'm connecting to the platform. So since right now I'm already a user in the platform, I'm directly connected to the platform. But if someone for the first time wants to connect, first thing is to go to the smart control INOWAS.com. So here, modeling platform, I direct to this point, and we go to start now. So here, what you see, all these models that you see, are basically different models that have been developed by me related with Ezousa. So as you can see here, because there are a lot of models, I choose to place them in the private space, which means that only me can see all these models. But there's also the option to move them to the public place where other users have also sent their models. So for the purpose of this tutorial, we are going to create the model, and to do that, to start doing that, we need to push the button which says create new. So as you can see here, I have the option to choose either the public or the private option. We choose the private options by deactivating the public option. So the name might be a characteristic name of what we want to do. In our case, we can simply say video for Ezousa catchment, and to customize it even more, we can also put the date. So here we also have we need to define the LED unit. Currently, the platform supports only meters as a unit, which is fine. It's appropriate for our purposes. And also time units in days. So also days is the only option here, which is again eligible for our purposes. And now we need to also define the start date and the end date. So in order to be consistent with the field measurements related with Ezousa, we are going to use realistic starting and ending dates. Basically, there was a period around 2002 when Ezousa was at the initial stage of its operation, and the Ezousa MAR system, where the wells and the infiltration basins were not yet implemented. And this period is assumed to be close to resembling a steady state period. So I'm going to assume that this is actually true for the purpose of this tutorial. And here I created a brief txt file in which I already wrote the starting and ending date. So it's from the 1st of October of 2002 and the ending date is 5th of June of 2003. Nice. So the next step is to create the computational domain, and for that purpose we need to create a polygon which will define the area of this domain. So this can be done with two ways. First one is to draw a polygon on a map. This is a quick solution, but it's limited regarding the accuracy, especially if you have to deal with complex geometries like the one we are going to use in Ezousa. And the other options, which is the one we are going to consider, is to load a polygon which is expressed in a GeoJSON format. So this is what we choose. As you can see here, you have two options to load the GeoJSON file. The one is open the GeoJSON file and copy paste the subset of the file which is needed in the platform. Here you can see the details of it. We need to define a polygon, and here are the coordinates which define the polygon. In this tutorial, we are going to consider for brevity only loads based on the file directly. So we need to select the file, and as you can see here, we're going to use the entire domain polygon. We open it, and so as you can see, it is in domain under consideration. Next, we need to push apply, and we're waiting for the model to be uploaded. As you can see here, the domain is enclosed inside a rectangular grid within which we see a gray color. So this is basically the region where we're going to define our grids. Since we are going to introduce this model for demonstration purposes, we don't need to go to a very refined grid. So we can just use one grid with 150 rows and 150 columns. As you can see here, this directly calculates the height and the width of each cell. So here we consider uniform grid, which means that the cells have the same size all over the rectangular domain. Here we have the option to rotate the rectangular grid, but currently we prefer not to. We don't need to do it. And this intersection number is basically a value between 0 and 1, which tells you basically how much fraction of a cell should be activated or not, based on if it's inside or outside the polygon, the computational domain. So the grid is created. We need to create the model now first. Now I can show you what I want to find out. So as you can see here, the active cell also are covering entirely the blue line, which defines the computational domain. This has to do with the intersection option. Basically, it tells you that the portion that you define, the value that you define from 0 to 1, says that if a cell, okay, this one I can describe it better at the final manual. Basically, it's a fraction which states how much portion of the cell should cover this line here. So if this cell, for example, has more than this value, its fraction of this cell covers more than this. Okay, we'll leave it for now. And so this is related with the spatial discretization. But now we need to define the time discretization. So the start and the end dates is already defined from before, the time units also. So this is a total time days between the start and the end date. So what we see here, basically, NSTP is the number of time steps, and this TSMULT is a time step multiplier. Basically, this value here defines a fraction between time step and its presenting time step. So if this value, for example, is more than 1, it means that the size of the time step is progressively increased, which means that the time steps at the beginning of the simulation are smaller than the time steps as we move towards the end of the as we move to subsequent time instants. This is reasonable in cases where we know that at the beginning of the time period we expect big changes, so we need a small size for our time step. And also we have the option to consider a steady or an unsteady simulation. So basically a steady simulation refers to the case where the transient term with the groundwater flow equations is removed. But in our case, since we are considering a number of stress periods, so our simulation evolves in time until it reaches eventually the steady period. This is also more stable in terms of computational stability. So we prefer to do it like this. So in our case, we are going to consider transient computations, which eventually reach after a sufficient period of time to the steady state solution. So since we have to consider many different stress periods, we are not going to do it manually using the options like this one, days, months, years, etc. Instead, we are going to import the stress period through a CSV file. So here we have the option to upload the file. So I'm going to use this CSV file, which as you can see has the same starting and ending time period. So firstly, we need to define the date time of the format. So we need to put the proper format to help you understand that. I will also open the CSV file. So as you can see here, the format is firstly years minus months minus days. So going here, years minus months minus days. Of course, the first row is a figure as you have seen. and then what we get is the start date time, the NSTP value. We have 300 time steps for this first period. The multiplier we mentioned before, and here the steady. So if the value is 0, it means that we don't have a steady simulation, that's a transient state. And this goes up to the last point, whereas is the end date here, where we don't put anything. Okay. So here we need to assign the columns. So as a start date time, we choose the column with the name start date time, NSTP with NSTP. In this case, for simplicity, we choose the column names to coincide with the ones needed from the platform, but in general you can put whatever you want, and even in different order columns, doesn't matter. And for the state. So as you can see here, the platform understands the format we gave it, understands that we are considering a transient simulation. We consider a constant time step during the stress period. We impose, for example, here 300 time steps for this period. So each stress period is considered to be 1 day. Some occasions we have used stress periods of 1 month, but because we wanted to keep the same time step, we just multiply the number of the time step with the number of the days. So now we push apply, and we see here that the values were properly loaded. So as you can see, we need to save the changes. So here the changes were automatically saved during the apply when we press apply. So now the next step is to import the different soil layers. So for our computations, we're going to consider only one vertical layer, which corresponds to an average layer in terms of the hydraulic and geological properties. So here we need to define the top elevation of the layer, the bottom elevation of the layer, horizontal conductivity, which has 2 directions. So let's say the XY plane, if this plane is assumed to be the horizontal plane, then we need to define both an X and Y component for the conductivity. This is done with the horizontal hydraulic anisotropy, which is basically a dimensionless value, which is basically giving you the ratio between the X over the Y component. So this is the vertical hydraulic conductivity, divided with the direction perpendicular to the horizontal plane. This is a specific storage, and this is a specific yield. These values are basically related with the accumulation of the hydraulic head, and are only meaningful when we consider transient computations. So the layer type have the options to choose either confined or convertible. We choose convertible, which means that the layer can be either confined or unconfined, depending on the values of the hydraulic head in a cell. So if the value of the head is larger than the top of the cell, it means that we are considering a confined layer. Otherwise, we are considering unconfined layer. So the layer average calculation is basically related with the calculations inside the internal flow. For example, related with the interblock conductance. So I'm not going to say more things about this. And we also have the rewetting capability, which states that if a cell becomes dry, then it can be rewetted depending on the hydraulic heads of the adjacent cells. So this option sometimes, on the one hand, it can provide you a more realistic situation, but on the other hand, can result to more unstable solutions. So for our case, we're going to leave it inactive. So now we need to start assigning values to every option, every property. So as you can see here, so here is a map. Here is a rectangular grid that we defined before. So we need to assign the elevation, which is expressed in meter above sea level. So in our case, we're again going to upload some raster files, which are created a priori about these QGIS purposes. So here is an interpolation method. We keep it as a nearest neighbor. Problem. So here we go to the soil layers, which is top layer. As you can see here, the values extend from close to 0, which corresponds to the region very close to the sea, up to 80 to 84 meters, which is the uppermost, basically the region where it's further away from the sea. Press apply. So as you see here, we get a flag saying that we need to save the change. So in some cases that you need to save everything at every step, some others is not needed, but in general you also need to keep in mind if it's necessary or not to do that. The best practice is to save as much as possible. And we do the same thing for the bottom of the page. Again, I'm going to load the TIF raster file. So here, as you can see, we can go even below the sea level, which is corresponds to the region close to the sea again. And again, as we go further away from the sea, we see that the values are increasing as expected. Okay. So now we need also to define the hydraulic conductivities, because the groundwater model needs both the difference between the bottom and the top elevation plus this value for the hydraulic conductivity to calculate the transmissivities, which are then used inside the groundwater equations in order to provide closure to the problem. So for this case, we have the option as before to either use some uniform values. In our case though, we decided to create some GeoJSON files again, polygons, uh, which give us more control over the conductivity zones. So we created 4 different zones for that purpose. So this is the first one, which is closed. Let's see. We have the same bounds as the model area. I don't know why this happens. Sorry, wrong. So we need to do it from here. Apologies. So we need to define zones. We need to go to the section named zones. So this is, as you can see, the line. It defines the outline of, the grid. So here we can load a GeoJSON. We also have the option here to do it by drawing the polygon, because this one identifies this reference value. But instead, we want to load some GeoJSON files. Again, here you can see some details of the GeoJSON file, but for simplicity, we are going to simply load them. So we go here, we upload the polygon. So as you can see here, these are the values. This is the region with the zone 1. And we apply. We expect, waiting for the platform to calculate the cells inside this zone. So save these changes. So we'll do that for the remaining 3 zones. So again, we have to also activate all the zones to see the overlap or to be able to identify any type of problems. So again, second zone. Here, select saturate zone 2. Apply. Nice. So we see now that the second zone is imported. So now we're going to add third zone. Again, I'm showing all the zones. File 3, select file. So reload saturate zone 3. Let's see this one here. Okay, and now the last one. Nice. This one It's faster. So now we have created the 4 different zones, and the remaining one is basically the default value which we are going to use. So now we'll go back to the layer, and we're going to assign different conductivity values to these zones. So as you can see here, we need to select the zones in which we're going to divide the different regions based on their conductivity values. So we want to use all 4 of these regions to cover the entire domain, as you can see here. So since we're doing this tutorial mostly for demonstration purposes, I'm going to assign some reasonable values that are based to the field measurements, meaning that the values close to the core should be lower than the values higher. So in previous times I did it with the drawing. It was giving a fair predictions. So in our case we're going to use for zone 4 around 100, and for the ones close around 30, but this is confusing a little bit for you, so I will just use the ones. So it's around 100. And this is around 50. So as you can see, the values close are around 30. Even here. So it increases in the middle around 50, and we go up to 100 on the upper part of the domain. And again, we need to save these changes. So Ezousa is assumed to be a homogeneous isotropic aquifer, which means that this value here, the horizontal and hydraulic anisotropy, should be defined equal to 1. And the same goes for the vertical hydraulic conductivities. So in our case, we will consider basically 2D simulations. Doesn't really matter. But for consistency, I'm going to use the same values. Right. So do it again to save the changes. Don't forget that. It's very important. So regarding the specific storage, this value is reasonable based on the calculations I've done, and also the values for the specific yield are reasonable. So we can also select our zones for each of these cases, but we will not do that. Doesn't really matter. So now we move to the next section. It is a boundary section. So if you remember, previously we mentioned that we're going to pose 2 no-flow boundaries at the 2 sides of the domain, and also we need to specify hydraulic heads at the coastal boundary and at the uppermost boundary. So this can be done by adding each by step by step the boundaries. So we have here a number of different boundary options, or for simplicity you can import these boundaries, again using a GeoJSON format. So we're going to follow this approach, and then after uploading the whole thing, we'll show you how you could do it without uploading the boundaries. So we go back, boundaries. So as you can see here, CHD boundaries, coastal, upper line. Now instead of doing that, actually, the platform gives you the option to upload everything that is related with the boundaries and also with the observation nodes. So as you can see, you have the option to upload them all together. Currently, this is how we can do it. So currently the platform does not support separate files. So you cannot upload one GeoJSON for the boundaries and another GeoJSON for the observation nodes. So you need to upload one that includes all this data gathered. So this is what we're going to do. So we're going to upload this. So until it's uploaded, maybe you can say a few things here. So what you see here, the BH means borehole, and this is the 4-digit numbers that define the different boreholes. So these boreholes here, as you can see, are the observation nodes that we will speak later on, which are distributed within the domain. And also, what you see here as a coastline is basically this boundary here along the coast. And we also have, you can see it here, the upper boundary. So I think I need to go out and enter again inside the model. So video for Ezousa catchment. So if I go here, you see, so it's synchronized, and the same goes for the upper part. So regarding the upper part, since we consider a steady simulation basically, so we need some constant values and during the entire time period. So what we did, we took all the values of the hydraulic head at the nearby well, and we obtained the average value of it during that time period. Fortunately, these values had small variations. Were varying from 74 to 81. So we assign a value equal to 77 for the entire time period. So after that, maybe the people maybe you already know, if you have used MODFLOW before, that if you don't impose any boundary condition on any other boundary surface, then MODFLOW understands that these boundary conditions is supposed to be a no-flow boundary condition. So you don't need to assign anything to the other two lines here. It does automatically by default. So now, through the GeoJSON file that we imported, we actually imported also the observation nodes. So these nodes basically are going to be used during the calibration process to compare the simulated values for the hydraulic head against the measured values of the hydraulic heads. So as you can see, we have chosen several nodes which are distributed along the computational domain. And so these are basically their actual names based on the data provided by the Water Development Department in Paphos, which is in charge of Ezousa Mar. So the type is HOB, OB for observation, H for heads. It's again assigned at the top layer, which is the only layer we have. So here you see that we have defined the latitude and the longitude. This is because currently the platform supports only WGS 84 as a geographical coordinate system, or you can, maybe some of you know that's EPSG 4326, and we have also assigned the observation values here. So we assume that we compare these values here at the end of the simulation period, where we are going to have a steady simulation and steady conditions for the simulation. And for that period, we know that the value, the observed value, is 7.52. So again, these values are actually average values, which were obtained from field values measured during this time period, so that it's meaningful to compare both of them together. Because as you remember, we have chosen, for example, for the upper part, an average value based on the different measurements during the time period and the entire time period. So now we go to the MODFLOW package. As you can see, we are using MODFLOW 2005, and you can go to the basic package. As you can see here, this is an active region where the equations are solved. So as a starting head, we are using the values of the top elevation. As you can see, 0 close to the coast and 84 at the top right part. So in our case, we need to choose proper values for the solver. So based on the USGS tutorial, as a simulation of the platform. we are ready to start the simulation. Do that, running the calculation process. So now the simulation is running. So until the simulation runs, we don't expect it to take for long, maybe a few minutes or even less. We see that the platform has additional functionalities. For example, you can also consider scalar transport. So in case you want to see the spatial temporal evolution of contaminants. We're not going to consider pollutants in the current manual. So, okay, I've seen that the computation has finished. So now we can go to the flow region. So as you can see, this is the initial distribution, and this is the final one. So currently we just see the final one, but in general you can see also the different periods. So you can see that we obtain a smooth solution here, which is what we expected. If you have the ability to see at the different times here, you could see that the value reaches basically more or less steady state, even from 100 or even 75 days. So we are confident that we have reached a steady solution. So basically what you see here is the horizontal and the vertical cross section. For example, if we move it like this here, so we can start from here. So while moving to a larger number of columns, so this is, let's say, column 1, 2, 3, and it goes up to 150. So here you see that we start from column 1, and at some point we enter inside the computational domain. That's why you see a non-zero values for the hydraulic heads. And then again, we move outside of the domain, that's why we don't see anything. So at the 63 column, then we come across with the vertical bar here. That's why you see this dashed vertical line. So a similar thing happens for the vertical cross section. So the rows start counting from here. The first one goes down to 150. Okay, so that's why we start from here, 0, this point here. So while we move down to that along this line, at some point we come across with the domain around row number 94, and inside this you see that the two lines intersect. That's why this dashed line is inside the blue area here, and afterwards goes again outside where no flow is present. So this is the contour map, and regarding the calibration, we see that the rule mean square error is around 6. Remember that the maximum value of the elevation is 77, and we get an R square of 0.9917, which is very good. So this value here could be actually done even smaller if we could actually make a finer mesh, because as you can see, the most important deviations between the simulated value and the observed is close to the coast. And in order to make this happen, we probably need more cells, because if you put more cells, then you allow to the hydraulic head to decrease even more, so that that way, by reducing the error in this region, by doing that, then you're automatically increasing the absolute mean square error. But it's not bad. It's I think the computations are reasonable, presentable, and they make sense. And based on the distribution of the conductivity values that also is based on the field measurements. So here's some additional values here. So it's the simulated heads and the residuals. We expect them to have low values. So I think our computational process has been described properly. We have reasonable results. So bye for now.